Welcome to Math TV with Professor V. In this video, we're going to continue looking at rational equations, but now through the lens of formulas, applications, and variation. Now, formulas occur in many situations. Sometimes it's useful to rewrite the formula, meaning that you solve it or isolate some other variable. And a formula is said to be solved for a specified variable if in that variable's only occurrence it appears alone on one side of the equal sign. So basically, whatever variable you're being asked to solve for, that variable needs to be all by itself on one side of the equation, and it better not pop up on the other side of the equation. Otherwise, you did it wrong. And many formulas involve rational expressions. And so in that case, we would typically begin by clearing denominators when you're trying to solve for a specified variable. Okay, so let's just get some practice here. Example, solve for the specified variable. In example A, it's asking us to solve for t, or to isolate t. Okay, well, look over here on the right-hand side of the equation where t is, and I'm noticing two main things that are keeping it from being in sweet solitude, in isolation. There's this v1 plus v2 in parentheses being multiplied by t, and then also I notice t is being divided by 2. So let's go step by step and remove each of those elements, right, that are on the right-hand side of the equation with t. So first thing, how about we multiply both sides by 2? Or 2 over 1, right? That way you can cancel out that 2 in the denominator. So now, bam, bam. On the right-hand side, it's gone. On the left, we have 2s equals v1 plus v2 times t. All right, good. And don't distribute through on the right-hand side, because remember, we're trying to get t by itself. So I actually want to get rid of v1 plus v2. Remember, that's being multiplied by t. So let's just go ahead now and divide both sides by v1 plus v2. And we're pretty much done. So notice here, v1 plus v2 cancels on the right-hand side. I have t all by itself. I'm going to put t on the left. So t equals 2s divided by v1 plus v2. And that's it. So let's go ahead and box it. We finished part A. Cool. All right, good. Let's move on to example B. In this case, it asks us to solve for P. All right, well, first thing I noticed, this is a rational equation because the variables, more than one variable, appears in the denominator. So think back to when we solved rational equations. If you forgot, I'll link the video right here. The first thing you want to do is clear your denominators, meaning you want to multiply by the LCD of the equation. So the LCD here is going to be PQR, and that distributes to each of the terms in the equation. Okay, good. Now this is PQR over 1 basically. So when I multiply PQR by that first term, by 1 over P, P cancels out. So I'm just left with Q times R plus 1 over Q, the Q will cancel out with PQR, so I'm just left with PR, and then this is going to equal, what should I have on the right-hand side? Very good, PQ. Okay, now go back, always remind yourself, check the directions. Which variable are we being asked to solve for? We're being asked to solve for P. So where is P? P is, I see 1 here, and then I see 1 more over here on the other side of the equation. So when that happens, the technique is as follows. You want to get all the terms that have P on the same side of the equation first. So let's move PR to join his little buddy PQ on the right. So I'll subtract PR. And now I have QR equals PQ minus PR. And the reason we do this is now all the terms that have P are on the right. I can factor P out of both terms on the right-hand side and I'm left with q minus r. And this is all equal to qr. All right, good. And then we're almost done. Remember, we're trying to get p all by itself. I'm going to divide both sides by q minus r, divide by q minus r, and then I can write my final result as p equals qr over q minus r. That process should remind you, if you think back to when we would find the equation for the inverse of a function, same process. Okay, now let's go ahead, look at example C. We're going to solve for t. Ooh, this is going to be a little tricky because notice there's t up here in the numerator, t down here in the denominator. So what we're going to do first, it's a rational equation. Let's get rid of the denominator. I'm going to multiply both sides by r minus t. So now we have k times r minus t equals r times t. And then let's go ahead, distribute through on the left-hand side. So we have kr minus kt equals rt. Good. Remember which variable we're solving for? We're solving for t. I see one over here and one over here. And think back to example B. You want whatever variable you're solving for all of the terms that have that variable to be on the same side of the equation. And then all the terms that don't have that variable, the ones that don't have t, have to get exiled to the other side. So I'm going to add kt to both sides. Okay. And then let's see what we're left with here. So now I have kr is equal to rt plus kt. And then I can go ahead, factor out a t here, and I have r plus k. So that's the whole point of grouping all the terms with t on the same side. You want to be able to factor it out. And then dividing both sides by r plus k will finish off the job, and t will be all by itself. So t equals kr divided by r plus k. And we are done. All right, good. So that's how to work with certain formulas that involve rational expressions and isolate variables. Now, variation problems are another situation where formulas involving rational expressions frequently occur. So there's a little bit of terminology you have to get under control in order to solve these problems. We say that y varies directly as x if one of those variable increases and the other one does also. So if as x increases, y does also. And you could write or express the relationship between these two variables using the formula y equals k times x. And k is our variation constant. It has actually a lot of different names depending on what textbook you're using. Some textbooks will call it the constant of variation constant of proportionality, something like that. Think back to when you were writing the equation of a line and you were trying to find the slope, right? Y equals mx plus b. K in some sense is just another constant, and each variation, each relationship between a set of variables has their own constant k that holds that relationship true. Okay, let's think of some variables, right, or some quantities that vary directly. Say you're thinking about the number of hours that you work and your paycheck, assuming you're not salary, right? If you work more hours, your paycheck should be higher. If you work less hours, your paycheck should be lower. Or think about it like the number of hours that you spend studying and your grade in your math class. I mean, they should be in direct proportion or direct variation. If you study more, your grade should go up. If you study less, your grade most likely goes down. Although there are exceptions to that. Okay. Now, we say y varies inversely as x if as x increases, then y decreases, or vice versa. So basically, when one goes up, the other goes down. And let's think of some scenarios where this is the case. Think about the number of miles that you drive and the amount of gas that's left in your tank. Right? The more miles that you drive, the less gas there is in your tank. So sad, especially right now because gas is super expensive. Okay, last option or definition is when you have variables varying jointly. So we say y varies jointly as x and z if basically the following relationship holds: y equals k times x times z. So I think of it as it's basically the same as directly. It's just you use the word jointly when there's more than one quantity or more than one variable interacting at the same time. Okay? Cool. So here's the steps to solving a variation problem. Define your variables and write the generic model. The generic model means write if it's going to be y equals kx, y equals k over x, etc. And we're not always going to use just y's and x's, okay? So be ready. And then plug in the given values and find the variation constant k. Your book might call k something a little different, but typically we use k for all these problems. Then you're going to write the equation of variation. So you're going to rewrite the generic model from step 1, but you're going to plug in whatever you got for k from step 2. And then the last thing, you're going to use the remaining information to solve the equation and answer the question. Usually there's going to be some sort of follow-up or something they want you to do in the problem, okay? All right, here we go. These aren't too bad, believe me. If z varies directly as x and z equals 30 when x equals 3, find z when x equals 4. Don't get that glazed look in your eyes just because there's words in a math problem, okay? Pull yourself together. You can do this. There's 3 parts here. Z varies directly as x. Z equals 30 when x equals 3. And then find z when x equals 4. We're going to go step by step. First step is write the generic model. So the problem tells me z varies directly as x. That means the generic model is going to be represented by z equals k times x because they vary directly. Okay, cool. Step 1's done. See, wasn't so bad. Now, next part, we need to find k. How do I find k? Don't worry, they're going to give you enough info so you can do it. It's right here, second part. Z equals 30 when x equals 3. So go back to that model in step 1. Z is 30 when x is equal to 3. So I'm going to substitute in 30 for z, 3 for x. Can you find k now? I hope so. Just divide both sides by 3 and we get that k is equal to 10. Very good. So this is our variation constant. That's not going to change. So step 3, you're going to write now the equation of variation. So basically you rewrite the equation from step 1, but now since I know k is 10, I'm going to replace that number into the model. Okay? Good. So this is our equation of variation. And that sometimes that's all you need to do. But look, they were especially demanding in this problem. And the last thing they asked us to do is find z when x equals 4. Okay, no problem, because now I've got my equation of variation. So I need to find z when x is 4. So z equals 10 times x, so 10 times 4. So z equals 40. And right now, I don't know what z and x represent, right? These are just variables that they're giving me arbitrarily, so we don't have to worry about putting units or whatever on them, okay? Good, very good. So hopefully that one was okay. We're gonna practice a few more until you guys become professionals. Yes, it's gonna happen. Next example, if a varies inversely, as b squared. Love it. And a equals 48 when b equals 4. Find a when b equals 7. Do you see how we have those same three main parts again? Okay. So step 1, let's write the generic model. It says a varies inversely as b squared. So inversely is when you have k over the other variable. So that means a equals k over, they're getting fancy, guys. Are you ready? B squared. Ooh, okay, okay. Step 2, we need to find k. How do we do that? They're always going to give you info so you can do it. Here's step 2's info right there. A is 48 when b is 4. Oh, okay. So 48 equals k over 4 squared. So that means 48 is equal to k over 16, right? How would I solve for k? I'd multiply both sides by 16 so that it cancels. And then we get that k is equal to 48 times 16. That's 768. All right. Then step 3, you're going to write the original model again, but now substitute in the value of k that you found. So you have the equation of variation. So we have a equals 768 over b squared. Boom. Box it if you want, because this is the equation or the formula that you're going to use now to answer the question in the last part. And the last part is here. It says find a when b is 7. So I'm just going to substitute in 7 for b. So we've got 768 divided by 7 squared. Okay. And that means a is going to equal 768 over 49. And just leave your answer like that. Whoa. I know this fraction is completely reduced, completely simplified, because remember 768, we got it over here from taking 16 times 48. And 7 doesn't divide into either of those. 7's not a factor of 768, so I know that that's totally reduced. I'm not going to write a decimal unless the directions tell me to, okay? Don't do decimals unless the problem starts with decimals already, or it tells you to round to 1 in the direction somewhere, okay? Good. How are you feeling? These aren't the worst word problems you'll run into, okay? They're rather tame. Let's do one where we get a little fancier. So find the variation constant. Who's that? Yeah, that's k. And the equation of variation if, okay, y varies jointly as x and z, and y equals 6 when x equals 4 and z equals 3. Okay, so for this one, they just want us to find k and the equation of variation. We don't have that fourth step of answering an extra question, so that's kind of nice. So let's go ahead and write the generic model. So they told me here y varies jointly as x and z. So do you remember how to express that relationship? Good. It's y equals k times x times z. Okay, then we need to go ahead and find k. And that's why they told me this info here that I highlighted in green. So y equals 6 when x equals 4 and z equals 3. So 6 equals k times 4 times 3. That means 6 equals 12k. Divide both sides by 12, so k is equal to 1/2. So there I've answered the first part of the question to find the variation constant. And then the last thing is we need to find the equation of variation. So just go back to your generic model from step 1. And I'm going to replace k now with 1/2. So y equals 1/2 times x times z. And we're done. Not too bad, right? As long as you remember what directly, inversely, and jointly all represent, you're in business, let me tell you. Okay, now it's also possible for a variable to vary directly and or inversely at the same time with more than one other variable. You'll see this in a lot of formulas and relationships in your physics and chem classes. And this is called combined variation. So let's look at an example just so you're ready when it comes at you. Find the variation constant and the equation of variation if y varies directly as x and inversely as w and the square of z. Woo, okay, we're stopping there. We're stopping there. So let's write out the generic model. So y varies directly as x. That's going to be represented by y equals k times x. And inversely as w. So in the same formula, you're just going to put over w and the square of z. So that's z squared. So don't write two separate equations, okay? Whatever varies directly, those variables go in the numerator. Whatever varies inversely, those go in the denominator underneath k, okay? Good. All right, now we can move on. So we have to find the variation constant k and then the equation of variation. And then here they're giving me all the info that I need. So y equals 4.5 when x is 15, w is 5, z is 2. Cool. So let's go ahead. For y, I'm going to replace it with 4.5 equals k times x is 15 over w is 5, and then z is 2. So 2 squared is 4. Okay, I love it. So we've got 4.5 equals 15k over 20. If I multiply both sides by 20, that's going to give me 15k equals 4.5 times 20. You don't need a calculator. Don't even think about it. 4.5 times 2 is 9, and then just add a 0, so that's 90. And then divide both sides by 15, k is 6. Okay, so that's the variation constant. And then the equation of variation is the last thing we need to find. So I'm just going to go back to the generic model here and then replace k with 6. So we have y equals 6x over wz squared. How'd you like that one? Do you feel fancy? I hope so. That was a good one. Okay. Now, the ideas of variation apply to many kinds of application problems. So in the next two examples, the variables will represent actual quantities, okay? So there's just going to be a little more words in the directions, but don't freak out. You can do this. Same setup, basically, okay? The number of calories burned while dancing, that's my favorite kind of exercise, is directly proportional to the time spent. Directly. It takes 25 minutes to burn 110 calories. How long would it take to burn 176 calories while dancing? Okay, so we have to define our variables first. We've got number of calories burnt and time spent dancing. So you can do X and Y if you want, but since we've been doing all sorts of funky variables in this section, let's spice it up. Let's let C equal the number of calories burned, and then T is going to be the time spent dancing. Okay, love it. So first thing, we need our generic model, and the problem told me that these two variables are directly proportional. So their relationship is going to be expressed as C equals K times T. And that makes sense, right? The longer you dance, the more calories you'll burn. Cool. Okay. Step 2, we're going to have to try to find K, and yep, they totally gave me info so I could do it. They told me it takes 25 minutes to burn 110 calories. You guys, obviously this is going to vary based on your body, right? And the intensity with which you dance, but just go with it for the sake of this problem. So 110 is equal to k times 25. And then let's go ahead, divide both sides by 25. And we'll reduce. So I can divide 110 by 5. It's going to go in 22 times, and then 25 divided by 5 is 5. So k equals 22 over 5. Okay, so step 3, let's rewrite the variation equation, but now I'm going to replace k with 22 over 5 times t. And then the last thing it asks is how long would it take to burn 176 calories while dancing? So now I'm going to replace c with 176, and that's equal to 22 over 5 times t. Well, how would I get t by itself? Divide both sides by 22 over 5. Or easier way to think of it is multiply both sides by 5 over 22, by the reciprocal. So multiply by 5 over 22. Okay, so cancel, cancel. Everything cancels out here. Bam, 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 bam. You have t all by itself. So t equals 5 times 176 over 22. And this comes out to 40. So what does that tell us? That tells us it takes 40, what units are those? Minutes to burn 176 calories. Okay. Hey, that's worth it. So don't go home from the club too early. Make sure you dance thoroughly. All right. Last one here. The time t required to empty a tank varies inversely as the rate r of pumping. You know what, let's just do step 1 now before we read too many words and get overclumped. Okay, so time t varies inversely as the rate r. They already told me what the variables represent, so I'm just going to write the generic model. T equals k over r. Good. If a Briggs and Stratton pump can empty a tank in 45 minutes, that represents t at a rate of 600 kiloliters per minute. That's r, that's my rate. How long will it take the pump to empty the tank at 1,000 kiloliters a minute? Okay, we'll worry about that later. Let's get k now. So step 2. They told me 45 minutes, so 45 for t is equal to k divided by 600. So I'm going to multiply both sides by 600, and k is equal to 27,000. Okay, so step 3, I'm going to go back to the original model from step 1. T equals 27,000. Divided by r, since I know that's what k is equal to now. And then we can go ahead and answer the question in part 4. It's asking us how long, so we need to find t, that's what we want to find, will it take the pump to empty the tank at 1,000 kiloliters per minute. So that represents the rate. That I'm going to plug in for r down here to find t. So t equals 27,000 divided by, the rate here is 1,000 kiloliters per minute. Oh my goodness, someone loved us. They gave us such nice numbers. We don't even need to get the calculator out. And we've got 27. 27 what? 27 minutes. Okay, good. So it takes 27 minutes. All right, so that concludes the lesson. Hope you found it helpful. These are super manageable word problems. Hopefully they'll help you build up your confidence so you won't be so terrified when you run into applications in the future. Okay, give the video a thumbs up, please, if you found it helpful. Subscribe if you haven't already. And stay tuned. We got more algebra coming your way, more stats, more everything. I'm a busy bee.